A 100,000-ton cargo vessel glides effortlessly on the water, while a single steel nail weighing a fraction of an ounce sinks like a stone. Looking at this 3D vector diagram, we can see the baseline for every object on Earth. Everything experiences a universal downward pull toward the planet's center. We call this force gravity. As an object's mass increases, that downward force grows. The specific, measurable pull of gravity acting on a given object is exactly what we define as its weight. This diagram illustrates another vital metric, density. It calculates exactly how much mass is packed into a specific volume. The general rule is simple. Pack those particles tighter than the surrounding water, and the object goes down. That explains the nail's trajectory. It is highly compact and incredibly dense. Its concentrated mass easily punches through the water's surface, overpowering any natural resistance from the fluid below it. Yet, military aircraft carriers are forged from the exact same metal. Based on the rules of density alone, hundreds of thousands of tons of steel should plunge to the ocean floor in seconds. For these decks to stay dry, an invisible upward force has to be fighting back against gravity. Anytime you place an object in a fluid, like water or air, that fluid pushes back. Physicists refer to this upward pressure as buoyant force, or upthrust. Notice what happens in this tank cross-section as the block is lowered inside. Two objects cannot occupy the exact same space. The block forces water out of the way to make room for its own volume. We call this displaced water. Fluid naturally seeks to return to its original resting place. All of that displaced liquid immediately tries to rush back in, pressing firmly against the bottom and sides of the intruding object. Whether an object sinks or floats comes down to a straightforward contest of forces. If an object pushes enough water out of the way, the resulting upward pressure will perfectly match its own downward weight. Around 250 BCE, the Greek scientist Archimedes successfully quantified this exact relationship. His principle dictates that the upward buoyant force acting on an object is exactly equal to the weight of the fluid that the object displaced. Look at this cross-section of a modern ship hull. Marine engineers solved the steel paradox by designing the hull as a thin metal shell surrounding millions of cubic feet of air. Wrapping that heavy steel shell around air drastically expands the ship's total volume. When you average the weight of the dense metal walls with the incredibly light interior, the vessel's overall density drops well below that of seawater. When it launches, the massive hull pushes thousands of tons of water out of the way. Because it occupies such a large volume, it eventually moves an amount of water that weighs exactly the same as the entire ship. This deep hull sits in perfect equilibrium. By manipulating geometry to command immense volume, engineers transform the ocean's own weight into a literal supporting pillar for thousands of tons of metal. This state of equilibrium has strict limits. Stack a vessel with heavily loaded shipping containers, and you add immense downward weight. The ship has no choice but to sink slightly deeper, displacing more water to find a new balancing point. Add too much cargo, and the downward pull of gravity will overpower the maximum possible upthrust of the hull. Maritime law strictly governs this math, requiring a load line, or plimsoll line, painted on every commercial hull to mark the absolute limit of safe displacement. Engineers can also use these laws in reverse. Submarines are built with specialized ballast tanks that intentionally flood with seawater or blow out compressed air. By actively dialing their internal density up or down, the crew can sink below the waves on command. Nature takes advantage of this same math. When liquid water freezes, its molecules spread farther apart. The ice expands, increasing its volume and lowering its overall density. That slight structural change allows millions of tons of glacial ice to drift entirely unsupported. From a drifting iceberg to a fully loaded naval fleet, every object in the water operates under this exact principle. The ability to cross the world's deepest oceans relied entirely on pushing aside just enough water to keep gravity in check.